Okay, everyone. Today, we're diving into the story of one of the most advanced machines ever built by humankind, the Wendelstein 7X stellarator. It's not a spaceship, not a particle accelerator, but something that could change everything about how we power our civilization. This is the frontier of fusion energy. Nuclear fusion is the same process that powers the sun. Two hydrogen nuclei merge to form helium, releasing huge amounts of energy in the process. The idea is simple, but the execution is brutal. You need temperatures of tens of millions of degrees, densities high enough for particles to collide, and magnetic fields strong enough to stop that plasma from touching the walls and destroying everything. That's what the fusion race is about, finding a way to bottle a piece of the sun safely and efficiently here on Earth. If we can do it, it means almost limitless clean energy. No carbon emissions, no long-lived radioactive waste, and a fuel source so abundant it's practically infinite. So far, the world has pursued two main approaches. The first is the tokamak, a donut-shaped reactor that uses powerful magnetic coils and an internal electric current to confine the plasma. It's the basis of projects like ITER in France. Tokamaks are relatively efficient but unstable. That plasma current can twist and buckle, causing sudden shutdowns known as disruptions. They also run in pulses rather than continuously. The second approach is the stellarator, a far more complex design that uses purely external magnetic fields, twisted, sculpted, and precisely shaped in 3 dimensions, to hold the plasma in place. No internal current, no major instabilities, and in theory, the ability to run indefinitely. The trade-off? The engineering challenge is staggering. That's where the Wendelstein 7X comes in. Built by the Max Planck Institute for Plasma Physics in Greifswald, Germany, it's the world's largest and most advanced stellarator. A superconducting labyrinth of 50 non-planar and 20 planar coils, frozen at -269 degrees C and powered by hundreds of megawatts of electricity. The goal is not to generate power yet, but to prove the stellarator concept works, to show that plasma can be confined, heated, and sustained long enough to make steady-state fusion a reality. Over the last few years, W7X has been gradually upgraded through a series of experimental campaigns. And in 2025, it broke through to something historic. Using a new high-speed pellet injector built at Oak Ridge National Laboratory, the team fired frozen hydrogen pellets directly into the plasma, feeding it continuously while the magnetic system held it perfectly stable. The result? A world record 43-second plasma discharge at over 30 million degrees, achieving a triple product performance level that finally put stellarators in the same league as tokamaks for confinement quality. That's not just a lab achievement. It's proof that steady-state fusion, the holy grail of energy research, is technically possible. For decades, fusion reactors have been limited by pulsed operation. A few seconds here, maybe a minute there. But Wendelstein's result shows that plasma stability can be sustained for nearly a minute without runaway instabilities, hinting at the prospect of continuous operation measured in hours or even days. If this can be scaled and optimized, the implications are enormous. Continuous fusion reactors could deliver clean baseload power without the intermittency of solar or wind. A single facility could power entire cities, desalinate oceans, or produce green hydrogen for global industry. Unlike fission plants, there's no chain reaction, no meltdown risk, and minimal waste. The fuel is hydrogen extracted from seawater. The byproduct is helium, the same gas that fills party balloons. 1 liter of seawater, if its hydrogen were fused, could in theory yield as much energy as 300 liters of petrol. The potential is almost limitless. But we're not there yet. Wendelstein 7X doesn't produce net energy. It still consumes far more electricity than the fusion reactions release. And there are major hurdles ahead. Plasma-facing materials that can survive constant neutron bombardment, heat exhaust systems that can handle hundreds of megawatts of thermal load, and the enormous engineering cost of scaling this complexity into commercial plants. Still, the direction is clear. Each new record, higher temperature, longer pulse, better confinement, marks one more step towards sustainable fusion. And while W7X continues its campaign, private companies are moving fast. Startups like Proxima Fusion are using its data to design commercial stellarators with advanced superconducting coils and AI-optimized geometries. The idea is to turn what was once a scientific experiment into a power station. If fusion succeeds, it reshapes everything. Energy abundance changes economics, geopolitics, and daily life. It makes desalination cheap, industrial heat carbon-free, and space travel practical. It could lift billions out of energy poverty and remove the resource pressures that have defined centuries of conflict. In short, fusion isn't just a new technology. It's a new phase of civilization. For now, though, humanity's miniature sun still burns behind magnetic walls in northern Germany. The Wendelstein 7EX isn't producing power yet, but it's teaching us how to. And every new pulse brings us closer to that future. A world where energy is infinite, clean, and everywhere. A world powered by the stars themselves. Future forged, where science meets civilization,